Space is the most hostile environment we have ever dared to enter. We see the breathtaking launches and the stunning images, but the true story of exploration is written in the shadows, in the perils no camera can capture. Beyond the silent vacuum and the obvious radiation, there exists a vast catalogue of hidden threats, each one a potential mission ender lurking in the darkness. Today, we pull back that curtain. By the end of this journey, you will understand the 30 most formidable and often overlooked dangers that astronauts and machines face among the stars. We will confront the silent rain of particles that shred human DNA from within, and the psychological abyss that opens when Earth is just a pale blue dot. What does it truly cost to reach for another world? The answer is far more complex and far more dangerous than most of us ever realize. Are we truly prepared for the price of stepping into the cosmos? Our journey begins not in the distant void, but in a cage of our own planet's making. Wrapped around the Earth like two colossal, invisible donuts are the Van Allen radiation belts. These are not empty zones of space, but furious rings of energy, where our planet's magnetic field has captured and concentrated a storm of solar and cosmic particles. Protons and electrons whip around at nearly the speed of light, creating a permanent, seething radiation environment that any spacecraft leaving Earth must first pass through. This is the first great gauntlet, a hidden moat defending the castle of our world. The danger here is not subtle. For an unshielded astronaut, a prolonged stay within the belts could deliver a lethal dose of radiation in a matter of hours, causing acute radiation sickness that would cripple a mission and end lives. This was the stark reality faced by the Apollo missions heading to the moon. Their solution was not to fight the belts, but to race through them. By plotting a trajectory that took them through the thinnest possible region of the outer belt and crossing quickly, they limited the crew's exposure to a manageable, though still significant, level. It was a calculated risk, a high-speed dash past a silent fire. Today, with plans for longer-duration lunar missions and space stations in high orbits, we cannot simply dash and hope. The Van Allen belts demand respect. Every modern mission must chart its course with surgical precision, and spacecraft shielding is designed with this specific, punishing environment in mind. It is a reminder that sometimes the first and most formidable wall we must scale is the one right outside our door, and this is merely the introduction to a far more pervasive and insidious threat. But the Van Allen belts are a local storm, a known danger we can map and navigate. The true, unrelenting background threat comes from much farther away. This is the second hidden danger, a silent rain that never ceases, galactic cosmic rays. These are not mere particles, they are atomic bullets. Imagine the nucleus of an iron atom or another heavy element, stripped of its electrons and accelerated across the galaxy to nearly the speed of light by distant supernova and black holes. They are unimaginably energetic, and they are everywhere, a constant, isotropic drizzle from all directions. When one of these microscopic projectiles slams into a spacecraft hull, it does not simply stop. It shatters, creating a secondary spray of even more particles in a process called a shower. Standard aluminum hulls, the kind used on the International Space Station or the Space Shuttle, offer little more than a speed bump to these cosmic bullets. They pass right through and through the bodies of the astronauts inside. The long-term cancer risk from this chronic exposure is the most well-documented threat, a statistical certainty that adds up with every day spent in deep space. But there is a more immediate and chilling possibility: central nervous system damage. Studies suggest that a direct hit from a heavy galactic cosmic ray particle to an astronaut's brain could damage neurons, potentially impairing cognitive function, causing memory lapses, or even triggering early-onset dementia years after the mission ends. This is the unsolved puzzle for engineers dreaming of Mars. How do you shield against something with the penetrating power of a subatomic freight train? Lead and concrete, our traditional radiation barriers on Earth, would be far too heavy to launch and could actually make the problem worse by generating more secondary particles. The solution might lie in innovative materials like water or polyethylene, or in creating magnetic force fields around spacecraft, but these concepts are still in their infancy. For now, galactic cosmic rays represent a fundamental hard limit, a background countdown clock that starts ticking the moment we leave Earth's protective magnetic embrace. Every mission planner for a journey to the Red Planet must look at that clock and ask, can we get there and back before the toll becomes too great? And while our bodies are under this invisible assault, our minds face a different kind of siege, one born from the very environment we seek to conquer. The silent, constant rain of galactic cosmic rays is a chronic condition of space travel, a slow, statistical threat. But the sun can unleash something far more acute and violent. This is the third hidden danger: solar particle events. While galactic cosmic rays are a distant, steady drizzle, solar particle events are a sudden, scalding downpour. They originate from the sun's immense fury, in explosions called solar flares and coronal mass ejections. These eruptions can blast billions of tons of solar plasma and a torrent of high-energy protons across the solar system at incredible speeds. For an astronaut, this is the difference between a long-term health risk and a potential immediate crisis. A major solar storm, if it hits a spacecraft directly, could deliver a radiation dose severe enough to cause acute radiation sickness in a matter of hours, threatening not just long-term cancer risk but the very survival of the crew. The danger is most extreme when astronauts are most exposed. Imagine an astronaut on a spacewalk performing critical repairs outside the International Space Station when a warning flashes from mission control. A coronal mass ejection has just been detected and the storm of protons is already on its way. They would have mere hours, sometimes less, to retreat to the safety of the station's hull. But what about a crew in transit to Mars, halfway between worlds with no large station to hide within? For them, survival depends on a dedicated storm shelter, a small, heavily shielded compartment within the spacecraft, lined with water or other protective materials where the crew would hunker down until the storm passes. This makes space weather forecasting not just a scientific curiosity, but a pillar of mission safety. Astronomers constantly monitor the sun for signs of unrest, watching for the telltale sunspots and magnetic activity that precede these eruptions. That warning time is everything. It is the difference between taking shelter and being caught in the open during a proton hurricane. Our ability to predict these solar tantrums is good, but not perfect, adding another layer of uncertainty to every journey beyond Earth's magnetic shield. We must listen to the sun's mood because when it rages, the entire inner solar system feels its wrath. And while we shield ourselves from these particle storms, another invisible force works to dismantle the very machines we rely on, piece by microscopic piece. Radiation is an invisible invader, but gravity's absence is a thief that steals from the body in plain sight. Our fourth hidden danger is the relentless systemic toll of microgravity. Every system in the human body evolved under the constant, gentle pull of Earth's gravity. Remove that foundational force, and the very architecture of our physiology begins to unravel. Two of the most critical and well-documented casualties are muscle atrophy and bone density loss. Without the daily work of standing, walking, or even just resisting gravity, muscles begin to waste away at an alarming rate. Astronauts can lose up to 20% of their muscle mass in just 5 to 11 days if they do not counter it, but the bones tell an even more startling story. On Earth, our skeletons are constantly remodeling, with cells breaking down old bone and building new material in response to stress. In microgravity, that balance is shattered. The breakdown process accelerates wildly while new bone formation slows to a crawl. The body, sensing it no longer needs a strong frame to hold itself up, begins leaching precious minerals like calcium directly from the bones, excreting them as waste. This isn't just weakening, it's a literal dissolution of the skeleton from within, with astronauts losing on average 1 to 2% of their bone mass every single month they are in space. For a mission to Mars, which could take over 2 years round trip, that adds up to a catastrophic 25% or more bone loss in some critical areas like the hips and spine. The countermeasures are as grueling as the problem itself. Astronauts on the International Space Station commit to over 2 hours of intense daily exercise, strapped into specialized resistance machines and treadmills, fighting just to slow the decay. But here is the sobering truth. This rigorous routine does not stop the damage, it only mitigates it. An astronaut returns to Earth after 6 months fundamentally weaker, with brittle bones and shrunken muscles, requiring months of painful rehabilitation to rebuild what was lost. For a crew landing on Mars after a long voyage, the danger is twofold. First, they would arrive in a severely debilitated state, less capable of performing strenuous surface tasks in bulky spacesuits. Second, and perhaps more frightening, is the question of readaptation. Martian gravity is only 38% of Earth's. Will a body that has spent years unraveling in zero-G even know how to rebuild itself under this new, weaker pull? Or will the deterioration simply continue, leaving explorers permanently crippled on a foreign world? We are fighting a war against our own biology, and so far we are only delaying the inevitable defeat. And as our bodies struggle against this unseen force, another silent phenomenon begins to play tricks on the very fluid that keeps us alive. The body's struggle against microgravity does not end with bones and muscle. There is a quieter, more insidious shift happening inside every astronaut, one that targets the very fluids that sustain life. On Earth, gravity pulls our bodily fluids downward, pooling them in our legs and lower torso. The heart works against this pull, pumping blood upward to the brain. But in the weightlessness of space, that fundamental tug disappears. The result is a massive, immediate redistribution. Fluids drift upward, equalizing pressure throughout the body. This causes the well-known puffy face and bird leg syndrome astronauts experience, where their faces appear swollen and their legs become noticeably thinner. While this might seem like a strange but harmless side effect, the real danger is what this fluid shift does to the most protected part of the body, the brain. The increased volume of fluid in the upper body raises the pressure inside the skull, a condition known as intracranial pressure. For months or years, this constant, abnormal pressure presses against the back of the eyeballs, literally reshaping them. This is the core of spaceflight-associated neuroocular syndrome, or SANS. The optic nerve, the vital cable that carries visual information to the brain, becomes swollen. The retina, the light-sensitive tissue at the back of the eye, can develop folds. The eyeball itself can flatten. The consequences are not theoretical. A significant number of astronauts return to Earth with measurable, and in some cases permanent, changes to their vision. They report blurred sight, a need for new eyeglass prescriptions, and a reduced ability to see objects up close. Imagine the implications: an astronaut navigating the complex controls of a spacecraft, reading critical data on a screen, or performing a delicate repair during a spacewalk relies on perfect visual acuity. Blurred vision in that environment is not an inconvenience, it is a direct threat to mission success and crew safety. The long-term health implications are equally troubling. We do not yet know if these ocular changes continue to progress after astronauts return to Earth, or if the damage fully heals. For those dreaming of multi-year journeys to Mars, SANS presents a frightening question. Could explorers arrive at the red planet with permanently degraded eyesight, unable to clearly see the new world they have traveled so far to reach? Countermeasures are being desperately sought, from specialized suits that create negative pressure on the lower body to pull fluids back down. to rigorous exercise regimens aimed at managing overall fluid balance. But as with bone loss, we are currently treating the symptoms of a problem rooted in the fundamental absence of gravity. The human body was never meant for this environment, and it is sending us a clear, disturbing message through our own eyes. And as our internal systems rebel, the very air we breathe in our sealed metal habitats becomes its own complex and fragile ecosystem, prone to silent, deadly failures. The human body's rebellion in space extends to its most critical defense network. Our sixth hidden danger is a stealthy weakening of the immune system. In the strange environment of microgravity, coupled with the constant stress of radiation, the body's intricate army of white blood cells and antibodies begins to falter. Research has shown that some key immune cells, like the natural killer cells that hunt down viruses and cancerous cells, become less active and less effective. It is as if the sentries on the walls have grown tired and distracted. This suppression creates a terrifying opportunity for enemies that were already hiding within. Latent viruses, like the various strains of herpes that most adults carry with no symptoms, often reactivate in astronauts. The body, which normally keeps these dormant passengers firmly under control, suddenly loses its grip. Astronauts frequently shed these viruses in their saliva and other bodily fluids, a clear sign their immune defenses are compromised. Now, combine this internal vulnerability with the external reality of a spacecraft. A crew lives in a sealed, recycled air environment for months or years. Every sneeze, every cough circulates. A common cold that would be a minor nuisance on Earth becomes a serious logistical problem, potentially sidelining a key crew member during a critical operation. But a more virulent pathogen, accidentally brought from Earth or cultivated in the unique conditions of the habitat, could spread rapidly through a crew whose bodies are literally less equipped to fight it. There are no hospitals in deep space, no emergency rooms on the way to Mars. A severe infection could deplete medical supplies, force a quarantine that strains team dynamics, and in a worst-case scenario, end a mission tragically early. We are sending explorers into the void with a body that forgets how to protect itself, while locking them in a can where disease cannot escape. The solution is not just better air filters, but a fundamental understanding of how to keep the human immune system vigilant in a place it was never meant to be. This biological fragility forces us to confront an even more fundamental question of survival in the void, one that begins with every single breath we take. This immune fragility is a quiet, internal war, but the mind wages its own battles against the vast emptiness outside. The seventh hidden danger is not a particle or a pathogen, but a profound psychological stress born from extreme confinement and isolation. Astronauts live and work inside a meticulously engineered tin can, but it remains a tin can, a fragile bubble of light and air separated from an infinite, lethal void by just a few inches of metal and glass. The initial wonder of the view, the life-changing perspective known as the overview effect, can give way to a crushing sense of distance. Earth is not just out the window, it is millions of miles away, a receding pale blue dot. The routine becomes everything, the same faces, the same walls, the same tasks day after endless day. In this pressure cooker, small irritations can magnify into major conflicts. A forgotten chore, a grating habit, a difference of opinion on a procedure, all of it unfolds with no possibility of stepping outside for a breath of fresh air or a moment of solitude. The risk of interpersonal strife is not just a discomfort, it is a direct threat to mission safety, where seamless teamwork is the difference between life and death. Depression and anxiety are constant shadows fueled by the relentless radiation exposure, disrupted sleep cycles from artificial lighting, and the sheer weight of responsibility. Communication with Earth offers a lifeline, but it is a flawed one. A video call home is a precious connection, yet it is also a painful reminder of everything and everyone you are missing. Worse, the time delay grows with distance. A message to Mars and back can take up to 40 minutes, turning a comforting conversation into a frustrating series of monologues. You cannot call for help in a crisis, you must wait for the answer to arrive. Crew selection is therefore a science of its own, seeking individuals with not just technical brilliance, but unparalleled emotional resilience, psychological stability, and an almost preternatural ability to get along with others in close quarters. Habitat designers work to include private crew quarters, windows with views of space or virtual nature scenes, and variable lighting to mimic a natural day-night cycle. But the stark truth is this: no simulation on Earth, not even a year-long stay in a remote Antarctic base, can fully replicate the psychological strain of a multi-year journey to Mars. You are committing to a voyage where you will watch your home world shrink to a star-like point where you will be utterly, irrevocably on your own. We can train the body and harden the machine, but can we truly prepare the human spirit for such absolute detachment? And as we manage the air, the water, and the minds inside the spacecraft, we must also confront the silent, corrosive chemistry happening all around them. The psychological strain of confinement is a battle fought within the mind, but outside the thin walls of the spacecraft, a physical storm is raging. Circling our planet at over 17,500 miles per hour is a growing cloud of our own making, a silent field of shrapnel known as orbital debris. This is the eighth hidden danger, and it turns the space around Earth into a cosmic shooting gallery. Every mission, every satellite, every rocket stage we have ever launched has left a trace. There are millions of fragments now, from defunct satellites and spent boosters down to flecks of paint, frozen coolant droplets, and even a lost glove or tool. The danger is not in their size, but in their speed. At orbital velocities, a paint chip just a few millimeters across carries the kinetic energy of a bowling ball thrown at 60 miles per hour. For the International Space Station or a crewed spacecraft, an impact from a piece of debris the size of a marble would be catastrophic, capable of penetrating hulls, shattering viewports, and severing critical systems. The windows of the space shuttle were routinely replaced after missions, pitted and scarred by tiny impacts from what engineers simply called space dust. To survive, spacecraft in low Earth orbit must constantly be on guard. An international network of ground-based radars and telescopes tracks tens of thousands of the largest objects, but millions more are too small to monitor yet still large enough to kill. When a potential collision is predicted, which happens with alarming frequency for the International Space Station, the only option is to fire thrusters and move the entire massive structure out of the way, a delicate and fuel-consuming dance with an invisible bullet. This constant vigilance is the hidden, daily tax of operating in space, but the true nightmare scenario is not a single impact. It is a chain reaction known as the Kessler syndrome, named for the NASA, a scientist who proposed it. Imagine if a collision between two large, derelict satellites shattered them into thousands of new fragments. Each of those pieces, now on its own chaotic orbit, becomes a new projectile, dramatically increasing the odds of further collisions. Those collisions would create even more debris in a cascading, exponential chain. One catastrophic event could fill a valuable orbital highway, like the paths used for Earth observation or communication satellites, with a dense, swirling cloud of shrapnel. That region of space would become effectively impassable, a permanent minefield that could destroy any new satellite or spacecraft that entered it. We would be trapped on our own planet, sealed off by a barrier of our own garbage. While this worst-case scenario is not yet a reality, the mathematical probability grows with every new satellite we launch, especially with the advent of massive commercial constellations numbering in the thousands. Cleaning up this mess is a monumental engineering challenge, with concepts ranging from nets and harpoons to giant lasers. But for now, the primary strategy is simply to avoid making it worse. The threat of orbital debris is a stark reminder that our greatest dangers in space may not be the mysteries of the universe, but the consequences of our own presence there. And as we navigate this man-made minefield, another environmental hazard works silently to dismantle our technology from the outside in. Orbital debris is a man-made hazard, but nature has its own version of this high-speed rain. The ninth hidden danger comes from micrometeoroids, the natural dust of the solar system. These are not fragments of old satellites, but ancient grains, often smaller than a grain of sand, left over from the formation of planets and comets. What they lack in size, they more than make up for in speed. While orbital debris zips around at staggering velocities, micrometeoroids can be traveling even faster, often exceeding 100,000 miles per hour as they cross paths with a spacecraft's orbit. At that incredible speed, a particle the size of a pinhead carries the kinetic punch of a hand grenade. The impact is not a simple hole, it is a violent, microscopic explosion. When such a particle strikes a hull, it and a portion of the hull material instantly vaporize into a superheated plasma, which then blasts outward, creating a crater far larger than the original projectile. A direct hit on a critical component, like a pressurized module or a fuel line, could mean a sudden, catastrophic decompression, but the more common threat is a silent, cumulative erosion. Imagine the surface of the spacecraft being sandblasted by an invisible, hypervelocity grit. Over time, this constant pitting degrades thermal coatings, clouds over viewports and camera lenses, and slowly eats away at the surfaces of solar panels, reducing their ability to generate power. The primary defense against this is ingenious in its simplicity, the Whipple shield. Named for its inventor, this is not a single thick wall, but a layered system. A thin outer bumper, often made of a material like aluminum or Nextel fabric, is spaced a few inches away from the main hull of the spacecraft. The idea is to let the micrometeoroid strike that first layer and vaporize. The expanding cloud of plasma then spreads out over a larger area before it hits the main wall, dissipating its energy and preventing a puncture. It is like using a shield not to stop a bullet, but to make it explode at a safe distance. This design is brilliantly effective for protecting the crew cabin, but it cannot be used everywhere. Vast, delicate structures like solar arrays, radiators that shed excess heat, and telescope mirrors must remain exposed to function. For them, there is no real shield. They simply endure the endless, silent peppering, their performance slowly, inevitably degrading with every microscopic impact over the years. This is the hidden tax of simply being in space, a slow-motion sandstorm that never stops, wearing down our machines one invisible grain at a time. And while the hull withstands this external abrasion, a different kind of decay is happening within, driven by the very environment we are trying to survive. The endless sandstorm of micrometeoroids is an external assault, but the surfaces of other worlds hide a far more clingy and intimate threat. Lunar dust is not like soil on Earth. Formed over billions of years by the constant hammering of micrometeoroids with no wind or water to soften it, each particle is a jagged, glassy shard. It is incredibly abrasive, capable of grinding down seals, clogging machinery, and scratching helmet visors into useless opacity after just a few moonwalks. But its most insidious property is its charge. Bathed in solar radiation and the solar wind, the dust becomes electrostatically charged, causing it to levitate and cling stubbornly to everything it touches. It coated the Apollo astronaut suits, working its way into joints and seals, and was tracked back into the lunar module, where it filled the air with a pungent, gunpowder-like smell. For a future lunar base, this dust is a nightmare. It will infiltrate every hinge, every airlock, every sensitive instrument. The real biological danger, however, comes from inhalation. These sharp, glassy fragments, if breathed into human lungs, could embed themselves deeply, causing inflammation and scarring in a condition similar to silicosis, a debilitating and incurable miner's disease on Earth. Martian dust presents all these same problems with a terrifying chemical twist. Analyses by landers have confirmed the presence of perchlorates, a class of chlorine-based chemicals that are highly toxic to the human thyroid gland. On Mars, this poison is mixed evenly throughout the global dust storms that can engulf the entire planet. For astronauts, tracking this toxic dust into a pressurized habitat is a direct contamination risk. It could coat surfaces, get into the air recycling system, and settle on equipment. Inhaling even tiny amounts or ingesting it from contaminated hands or food could lead to serious health problems over time. This means any mission to the Martian surface must treat the dust not just as a nuisance, but as a hazardous material. Spacesuits would need to be decontaminated in a special airlock before removal, a complex and time-consuming process after every single excursion. The dream of walking on another world comes with a hidden price, a constant, gritty battle against a toxic environment that wants to come home with you. That toxic dust is a tangible enemy, something you can see and feel. But the ultimate, ever-present threat in space is nothing at all. Danger number 11 is the vacuum itself, the profound and absolute absence of pressure. We all know the basic horror: a hull breach leads to explosive decompression. But the true danger is often more insidious than that single, catastrophic moment. Imagine a tiny, almost imperceptible leak in a seal around a viewport, or a microscopic crack in a weld developed from years of thermal stress. The air doesn't rush out in a violent gust, it whispers away, molecule by molecule, over days or weeks. Pressure sensors might detect the slow drop, but finding the source of such a leak in the complex maze of a space station's interior could be a maddening, time-critical scavenger hunt. All while the crew's precious, finite atmosphere steadily drains into the void. But let's confront the visceral reality of what happens if that barrier fails completely. In the near-perfect vacuum of space, the pressure holding your bodily fluids in a liquid state vanishes. The result is a condition called ebullition. The saliva on your tongue, the moisture in your eyes, and the fluids just beneath your skin begin to boil, not from heat but from the lack of surrounding pressure. Your body would swell to perhaps twice its normal size, though your skin and circulatory system are strong enough to prevent you from literally bursting. Consciousness would last for only about 10 to 15 seconds as the oxygen leaves your bloodstream and your brain shuts down. It is a brutal, unforgiving end. Yet, remarkably, it is not instantly irreversible. In 1965, at a NASA facility, a technician testing a spacesuit in a vacuum chamber experienced a sudden loss of pressure. He was exposed to a near vacuum for roughly 30 to 40 seconds before the chamber could be repressurized. He passed out, but he survived. He reported that the last thing he felt before losing consciousness was the saliva boiling on his tongue. This incident proved a critical, if grim, point. A rapid response can mean the difference between a tragic accident and a recoverable emergency. This is why every spacecraft is designed with compartmentalization. Hatchways can be sealed to isolate a breached section, and crew members train relentlessly for emergency repressurization drills. But it underscores a fundamental truth of spaceflight. Every seal, every valve, every hatch and weld is a single point of failure standing between the crew and oblivion. The vacuum is not an active force that attacks, it is an infinite, patient nothingness that is always waiting for the slightest weakness. We fill our fragile bubbles with air and life, knowing that the silence outside is the most demanding enemy of all. And while we guard against this ultimate loss of pressure, we must also manage the relentless and peculiar physics of temperature in a place where there is no air to carry heat away. The vacuum's silence is matched only by its utter indifference to temperature. In space, there is no air to gently distribute warmth or coolness, no atmosphere to moderate the sun's fury. This creates the 12th hidden danger, a violent cycle of extreme thermal fluctuations. An object in direct, unfiltered sunlight can be heated to well over 250 degrees Fahrenheit, hot enough to boil water. Just a few feet away, in shadow, that same object can plummet to minus 250 degrees, colder than the surface of Pluto. A spacecraft in low Earth orbit experiences this brutal swing every 90 minutes as it passes from day to night and back again. For engineers, this is a relentless war on two fronts. They must design systems that can absorb and reflect incredible heat on one side, while simultaneously generating and retaining enough warmth on the other to prevent critical components from freezing solid. This is achieved through a delicate ballet of technologies: white or mirrored coatings to reflect sunlight, radiators to bleed off excess heat, and electrical heaters to warm essential parts. But the constant expansion and contraction of materials is a hidden, grinding stress. Metal joints, seals, and wiring flex with every orbit, a process called thermal cycling. Over thousands of cycles, this can lead to metal fatigue, tiny cracks that grow, and the eventual failure of a critical seal or structural component. The danger becomes even more acute during surface operations on an airless world like the Moon. An astronaut standing in sunlight is baking in a suit that must actively cool them. But if they step into a shadow, perhaps inside a crater where the sun never reaches, they are instantly in a deep freeze that threatens to overwhelm the suit's heating systems. The line between these two extremes, called the Terminator, is razor sharp. One boot could be in searing light, the other in absolute cold, creating a nightmarish thermal management challenge for the life support system. Every mission must be choreographed around these thermal realities, a constant dance to keep machines and humans within a narrow, survivable band between the fire and the ice. The silent vacuum and thermal extremes are constant physical threats, but a more subtle danger erodes the very lifeline of a mission. Danger 13 is the tyranny of distance, manifesting as communication delays and blackouts. On Earth, mission control is a real-time partner, a collective brain trust that can see data, diagnose problems, and talk an astronaut through a crisis. This safety net vanishes beyond the Moon. The speed of light, while astonishingly fast, is not instantaneous. For a spacecraft on its way to Mars, radio signals can take up to 22 minutes for a simple one-way trip. A question from the crew, followed by an answer from Houston, means a conversation with a 44-minute pause between sentences. Imagine a critical system failure, an alarm blaring on the console. The crew cannot call for help. They must assess the situation, interpret the data, and decide on a course of action entirely on their own, knowing that by the time Earth even hears about the problem, they will have already either solved it or been consumed by it. This forces a profound shift in the very philosophy of mission control. They must transition from micromanagers to distant consultants, providing general guidelines and pre-approved procedures, then trusting the crew to execute with flawless judgment. The psychological weight of this autonomy is immense. Every decision, every repair, every medical intervention rests solely on the shoulders of the few people inside that metal hull. But there are moments when even that delayed connection is severed completely. These are communication blackouts caused by solar conjunction. When Mars passes almost directly behind the Sun from Earth's perspective, our star's immense radio noise and charged plasma overwhelm any signal trying to pass through. For weeks at a time, the crew is utterly, completely alone. No status updates, no news from home, no comforting voice from mission control, not even a delayed one. It is radio silence imposed by the cosmos itself. During these periods, the spacecraft must be a perfectly self-sufficient world, and the crew must become an independent civilization of a handful of souls, navigating the void with only their own training and each other to rely on. This isolation is the ultimate test of preparation, proving that for humanity to become an interplanetary species, we must learn to let go of the hand that has always guided us from the ground. That profound isolation forces a crew to become their own engineers, doctors, and first responders. The 14th danger is a brutal truth of spaceflight, the absolute reliance on complex, unserviceable machinery. In the void, there are no tow trucks, no hardware stores, and no overnight delivery for spare parts. Every whirring pump, every circuit board, every valve and filter inside a spacecraft must operate flawlessly for years, subjected to relentless radiation, thermal stress, and vibration, with no possibility of a mechanic's hands-on repair. This transforms every piece of hardware from a simple component into a potential mission-ending time bomb. The greatest threat often lies in what engineers call a single-point failure, a critical component with no backup. If that one part breaks, the entire system it supports collapses. A single faulty sensor could misread cabin pressure, a stuck valve could cripple a cooling loop, or a short circuit in the wrong wire could black out an entire module. The solution to this is the philosophy of redundancy, building in multiple, independent backups for every vital system. A spacecraft might have 3 separate computers that constantly check each other's work, or dual sets of thrusters, or quadruple redundant oxygen generators. But redundancy has its limits. It adds immense weight, cost, and complexity. You cannot have a backup for every single one of the millions of parts in a modern spacecraft. This is where the story of Apollo 13 becomes the ultimate lesson. When an oxygen tank exploded 200,000 miles from Earth, it wasn't a redundant system that saved the crew. It was raw, desperate ingenuity. The astronauts and mission control engineers on the ground had to become instant inventors, jury-rigging solutions with only the spare parts and tools already on board the crippled spacecraft. They famously used plastic bags, cardboard, and duct tape to build a carbon dioxide scrubber adapter, a literal life support system crafted from scraps. That mission proved that while redundancy can protect you from expected failures, survival often depends on the human ability to improvise, to see a collection of unrelated parts not for what they are, but for what they could become. For a crew bound for Mars, this reality is magnified. The spare parts they carry must be chosen with agonizing precision, and their training must include not just following procedures but rewriting them on the fly. They are not just pilots and scientists, they are the ship's entire maintenance crew, facing the chilling knowledge that the next critical failure might require them to invent a solution that has never been written down. Improvisation can save a mission, but some failures offer no second chance. Danger 15 is a nightmare that haunts every mission planner, the unique and terrifying risk of fire in a sealed, oxygen-rich environment. On Earth, our atmosphere is only about 21% oxygen, but inside a spacecraft, engineers face a difficult trade-off. To keep the cabin pressure comfortable without requiring impractically thick hulls, many spacecraft, including the International Space Station and the old Space Shuttle, use a lower overall air pressure. To compensate and ensure astronauts get enough oxygen to breathe, the percentage of oxygen in that air is raised. This creates what is called a higher oxygen partial pressure, meaning the actual number of oxygen molecules available for combustion is similar to, or even greater than, what we have at sea level on Earth. The consequence is stark. In this environment, materials that would not normally burn become dangerously flammable. A stray spark, a short circuit, or an overheated wire insulation can ignite a blaze that spreads with horrifying speed. This theoretical danger became a visceral reality aboard the Russian space station Mir in 1997, during a routine experiment using an oxygen-generating canister called a solid fuel oxygen generator. A faulty seal led to a rupture. The canister, essentially a chemical candle, erupted into a jet of flame over 3 feet long, spewing molten metal and filling the module with thick, toxic smoke. The crew, their visibility reduced to zero, struggled to don breathing masks and fight the fire with extinguishers. For several agonizing minutes, they faced the very real possibility of being forced to abandon the entire station, with no immediate way to return to Earth. They managed to put it out, but the event left the station severely contaminated with soot and corrosive chemicals, a grim testament to how quickly routine can turn to crisis. Fire in space is not just more likely to start, it behaves in alien ways. In microgravity, there is no up or down for hot air to rise. Flames do not flicker upward in familiar tongues. They form strange, stationary spheres of blue fire, lingering around their fuel source and consuming oxygen in all directions. This makes them harder to detect with traditional smoke detectors designed for Earth and far more difficult to fight. An astronaut cannot simply aim an extinguisher at the base of the flames because there is no base in the conventional sense. The fireball just hangs there, a deadly, suspended inferno. Suppression systems must flood an entire module with a chemical like carbon dioxide to snuff it out, a blunt instrument that also renders the air unbreathable, forcing a rushed evacuation. Every wire, every piece of fabric, every item packed for a mission is scrutinized for flammability, but the fundamental truth remains: to keep humans alive, we must fill their fragile home with the very element that makes catastrophe so easy to ignite. Fire's toxic aftermath is a clear and present danger, but a more subtle biological threat travels with every mission, unseen and silent. This is the 16th danger, the dual specter of contamination. The cosmos is not a sterile place, and as we reach out to touch other worlds, we risk becoming agents of biological pollution. This risk flows in two terrifying directions. The first is forward contamination, the accidental export of Earth's life. Our spacecraft, no matter how meticulously cleaned, are teeming with microbial stowaways. Bacteria like Deinococcus radiodurans are legendary for their ability to survive the vacuum, radiation, and temperature extremes of space by hibernating in a dormant state. If these hardy Earth microbes were to hitch a ride to a place like Mars and survive, they could utterly ruin our greatest scientific quest, the search for indigenous alien life. Imagine a rover scooping up soil and detecting organic molecules, only for scientists to realize too late that they were reading the signature of a bacterium from Florida that had clung to the drill bit during assembly. To prevent this, spacecraft bound for sensitive areas, like the icy moons of Jupiter thought to harbor subsurface oceans, undergo a rigorous sterilization process called planetary protection. Components are baked in ovens, cleaned with powerful chemicals, and assembled in pristine clean rooms. The goal is not to achieve impossible perfection, but to reduce the microbial load to an acceptably tiny number, a calculated gamble to preserve the virginity of other worlds for science. But the reverse scenario, back contamination, is the stuff of science fiction nightmares. What if we were to bring something back? The fear is not of little green men, but of a microscopic alien pathogen, an organism with a biochemistry so foreign that our immune systems would have no defense against it. While the likelihood of such a thing existing on Mars is considered low by most astrobiologists, the potential consequences are so catastrophic that the risk cannot be ignored. This is why the Apollo astronauts returning from the Moon were immediately sealed in a mobile quarantine facility, a modified trailer, until scientists were confident they posed no biological threat. For a future Mars sample return mission, the protocols will be far more extreme. The capsule containing the Martian rocks will likely be treated as the most hazardous material on Earth, diverted to a specialized maximum containment lab, a biosafety level 4 facility with multiple airlocks, negative pressure, and scientists working in sealed suits. The samples themselves may be sterilized with heat or radiation before any hands-on analysis begins, a frustrating but necessary step that could destroy the very evidence of life we seek. This is the profound paradox of exploration. Our desire to discover life elsewhere is matched only by our terror of what that discovery might mean. We must touch other worlds with clean hands, and we must be prepared to treat whatever we bring back as if it were the most dangerous substance in the universe. The sterile protocols of planetary protection guard against invisible invaders, but they offer no defense against a more familiar crisis. A medical emergency in deep space is a scenario stripped of all safety nets. Astronauts receive extensive first aid and basic medical training, but they are not surgeons. They are engineers, pilots, and scientists who must suddenly become emergency room doctors, with a pharmacy the size of a small cabinet and a diagnostic manual written for the worst day of their lives. Every gram of medical supply, from bandages to antibiotics, is weighed against the mission's other critical needs, resulting in a brutally limited inventory. There are no MRI machines en route to Mars, no blood banks, and no possibility of a medevac. A severe infection, a ruptured appendix, or a traumatic injury from a tool accident becomes an existential threat. The crew must diagnose, treat, and manage the patient entirely on their own, knowing that the nearest hospital is millions of miles and many months away. This forces agonizing ethical calculations long before launch. Which procedures do you train for? Do you include equipment for a dental root canal or materials for setting a compound fracture? Every addition is a trade-off, and every omission is a potential death sentence. The isolation transforms medical care from a service into a grim resource management puzzle, where the health of one can jeopardize the survival of all. And the environment itself conspires against even the most basic care. Performing something as routine as an injection or stitching a wound becomes a surreal challenge in microgravity. Blood and other bodily fluids do not drip, they coalesce into hovering crimson globules that drift through the cabin, threatening to contaminate equipment and air filters. Surgical tools, if not meticulously tethered, will float away from the operating field. Imagine trying to maintain a sterile field when every stray droplet and instrument defines its own path through the air. Procedures we take for granted on Earth, like using gravity to drain a wound or keep a clear field of view, become impossible. Research into surgical techniques for space is in its infancy, exploring concepts like enclosing a patient in a clear, sealed tent to contain fluids or using magnetic tools that can be anchored. But these are prototypes, not proven solutions. In the face of a true surgical emergency, the crew might have no option but to rely on telemedicine, a heartbreaking exercise in delayed guidance. A crew member could strap on a camera and describe what they see, while a surgeon on Earth watches the feed 20 minutes later, then transmits step-by-step instructions that arrive another 20 minutes after that. The person holding the scalpel would be operating on instructions that were based on what the patient's condition was 40 minutes in the past. This lag turns every decision into a gamble and turns the most skilled Earth-based surgeon into a helpless spectator of a tragedy unfolding in slow motion. The logistics of space medicine force us to confront a raw truth. We are sending explorers into the void with a medical safety net made of little more than hope, ingenuity, and a very short list of supplies. A medical crisis highlights the fragility of the human body in space, but survival depends on more than emergency care. It requires a steady, reliable supply of the right kind of fuel. Danger 18 is the slow creep of nutritional deficiencies and the fragility of our food systems beyond Earth. We cannot simply pack a few years' worth of military rations and call it a day. The food astronauts eat must sustain them physically and psychologically over voyages that could last 1,000 days or more. The first challenge is the silent degradation of the food itself. Even with advanced preservation techniques like freeze-drying and thermostabilization, vitamins and other essential nutrients break down over time, especially under the constant bombardment of space radiation. A sealed pouch of food might still look and taste acceptable after 2 years, but its nutritional value could have plummeted, leaving astronauts vulnerable to conditions like scurvy. a disease caused by vitamin C deficiency that humanity conquered centuries ago on Earth, only to potentially rediscover it on the way to Mars. This makes resupply missions or carefully planned consumption timelines absolutely critical for any long-duration mission, but the problem runs deeper than chemistry. Food is a profound psychological anchor, a piece of home and normalcy in an utterly alien environment. Monotonous, unappetizing meals can lead to what astronauts call menu fatigue, where crew members simply stop eating enough because they cannot face another identical packet of mush. The resulting calorie deficit leads to weight loss, lethargy, and a further weakening of bodies already under assault from microgravity. To combat this, space agencies invest enormous effort into creating varied, culturally relevant menus and even including occasional fresh treats delivered by cargo resupply ships. For journeys beyond Earth's orbit where resupply is impossible, the proposed solution is bioregenerative life support, growing plants on board to recycle air, purify water, and provide fresh food. It sounds like a perfect, elegant cycle, but it introduces a terrifying new vulnerability: crop failure. A single pathogen, a flaw in the lighting or hydroponic systems, or an unexplained blight could wipe out an entire harvest in the confined ecosystem of a spacecraft. If your food supply is also your air and water recycling system, a failure is not just an inconvenience, it is a cascading, multi-system catastrophe. Malnutrition would set in long before the oxygen ran out, sapping the crew's strength and cognitive ability precisely when they would need it most to repair the failing systems. Ensuring a crew arrives at another planet healthy and alert means solving a problem we thought we mastered millennia ago: how to reliably feed ourselves, this time inside a sealed can hurtling through a radiation-filled void. All those life support systems, from air scrubbers to food supplies, share one brutal, non-negotiable requirement: they must be lifted off the Earth. This introduces a danger not of biology or radiation, but of pure, unforgiving mathematics. The 19th hidden danger is the tyranny of the rocket equation. This is not a single component that can fail, but a fundamental law of physics that governs every gram that leaves our planet. To reach orbit, a rocket must achieve a speed of roughly 17,500 miles per hour. To do that, it needs fuel, but the fuel itself is heavy, so you need even more fuel just to lift that initial fuel. And then you need fuel to lift that fuel. This creates a vicious, exponential cycle. The result is staggering. To launch a single kilogram of payload, like a camera or a liter of water, into orbit, you need to burn roughly 20 kilograms of rocket propellant. For a mission to Mars, the numbers become almost fantastical. The final spacecraft that lands on the red planet might weigh 50 tons, but to get that 50 tons on its journey, you need to start with thousands of tons of rocket and fuel back on the launch pad. This mathematical tyranny forces every mission planner into a series of brutal, dangerous trade-offs. Want thicker radiation shielding for the crew cabin? That's more mass. Need to carry more spare parts for critical systems. More mass. Dream of a larger medical bay or a more robust greenhouse. More mass. Every single safety margin, every ounce of redundancy, every comfort for the crew is weighed on a cosmic scale against the fuel required to lift it. This is why spacecraft are marvels of minimalist engineering, where every screw and wire is scrutinized. There is no room for just in case. The rocket equation dictates that to add 1 kilogram of safety equipment for the journey, you might have to subtract 2 kilograms of scientific instruments or accept a thinner hull. It is a hidden danger that underpins every other danger we have discussed because it directly limits our ability to protect against them. We cannot simply build a fortress-like ship for Mars. We must build the lightest, most fragile vessel that can possibly survive the trip, constantly balancing risk against the immutable laws of propulsion. Every mission is a high-wire act with the rocket equation holding the pole, reminding us that in space, the greatest enemy is often the sheer, crushing weight of the journey itself. The rocket equation dictates what we can lift, but a more abstract law governs where it all goes. Orbital mechanics is the silent, unforgiving mathematics of motion in a gravity well, and a tiny miscalculation within its rules can doom a mission as surely as any hull breach. This is the 20th hidden danger, the peril of trajectory errors. In the frictionless void of space, there is no coasting to a stop, no pulling over to check the map. Every action, every tiny burst from a thruster, commits you to a new path that curves across the solar system under the relentless pull of the sun and planets. The most critical moments are the course corrections, the precise engine burns that nudge a spacecraft onto its interplanetary highway. These maneuvers are measured in delta V, a term for the precise change in velocity. The margin for error is vanishingly small. An engine burn that delivers just 1% too much thrust or points a fraction of a degree off course might seem trivial in the moment. But over the millions of miles to Mars that microscopic error compounds, it is the cosmic equivalent of aiming a rifle at a target a mile away, where a tremor in your finger at the trigger pull means the bullet misses by 100 feet. For a spacecraft, that miss is measured in millions of miles, flying past the target planet into the endless dark, with far too little fuel left to turn around and correct the mistake. This razor's edge is sharpest during one of spaceflight's most elegant and perilous tricks, the gravity assist. To save immense amounts of fuel, mission planners use planets as gravitational catapults. A spacecraft approaches a world like Venus or Jupiter, skims past it at a precisely calculated angle, and steals a tiny fraction of the planet's orbital momentum to boost its own speed and change direction. It is a celestial slingshot, but the precision required is staggering. To achieve the desired trajectory, the spacecraft must hit an imaginary keyhole in space, a target zone perhaps only a few dozen miles across, while both it and the planet are moving at tens of thousands of miles per hour. Miss that keyhole by even a little and the slingshot fails. You might be flung in the wrong direction entirely or sent careening into a solar orbit from which there is no return. The Voyager probes performed a breathtaking series of these assists to tour the outer planets, a feat of navigation so precise it was compared to threading a needle from across a continent. Every mission that leaves Earth's orbit is a prisoner of these perfect calculations. There are no guardrails, no friction to slow you down, and no second chances. A single decimal point out of place in the flight computer can write an epitaph for a billion-dollar mission, lost not to explosion or failure, but to a silent, uncorrectable drift into the wrong part of the sky. The mathematics of orbital mechanics delivers a spacecraft to the doorstep of another world, but the final step is a leap into the unknown. Danger 21 is the peril of landing on uncharted terrain. For a robotic probe or a future crewed vehicle, this culminates in the infamous 7 minutes of terror, the harrowing descent through an alien atmosphere where communication is blacked out and every action must be performed autonomously with no chance for human intervention. But the terror does not end at touchdown. The true danger lies in the final feat, when the vehicle must find a safe spot on a surface we have only mapped from orbit. Cameras and radar scan the descending ground, comparing it to onboard maps to avoid the worst hazards, but the resolution has limits. A landscape that looks smooth from hundreds of miles up can be a jagged nightmare at human scale. This was the stark reality for the Mars Perseverance rover. It was targeted at Jezero Crater, an ancient river delta that once held a lake, a perfect site to search for signs of past life. From orbit, the landing zone appeared manageable, but as the rover descended, its hazard detection system saw a field of boulders, treacherous slopes, and sand pits that could have swallowed it whole. At the last possible second, the onboard brain executed a lateral maneuver. literally flying sideways to place the rover down in the only safe patch within its reach. It was a brilliant success, but it highlights the razor-thin margin for error. A single sharp rock hidden by dust or just beyond the resolution of the maps can rupture a landing leg or pierce the belly of a spacecraft. A slope just a few degrees too steep can cause a vehicle to tip over, rendering it immobile and doomed. The dust itself is a trap, as landers like the Phoenix spacecraft discovered when they touched down on what turned out to be a hard, icy layer just beneath a thin blanket of soil. For a human mission, the stakes are unimaginably higher. The landing site must not only be safe for a much larger, heavier vehicle, but it must also offer resources, exploration potential, and a viable location for a base. Choosing that site is a gamble with human lives, balancing scientific reward against the very real possibility that the first boots on Mars could touch down next to a crevice or on a slab of rock that collapses under their weight. Every landing is a high-stakes blind date with another world, where the first intimate contact could be a fatal embrace. Landing safely is only the beginning of the battle on Mars. The planet itself holds an environmental fury that can engulf an entire world. Danger 22 is the Martian global dust storm. Unlike the brief, localized dust devils we see, Mars is capable of generating storms of biblical scale. It begins in the southern hemisphere's summer when increased solar heating stirs the thin atmosphere. A single local storm can grow, feeding on itself, until it wraps around the entire planet in a towering, opaque shroud of fine, rust-colored dust. These events are not mere sandstorms, they are planetary weather events that can rage for months, blotting out the sun and transforming the landscape into a perpetual, featureless twilight. For any mission relying on solar power, this is an existential threat. As the sky darkens, the energy needed to run heaters, life support, and communication equipment slowly drains away. Batteries can only last so long, but the danger is more than just a loss of power. The dust itself is an abrasive, invasive force. It coats every surface, seeping into joints and mechanisms. For a rover or a habitat, the static electricity generated by billions of colliding dust particles can pose a serious risk to sensitive electronics, potentially causing shorts or corrupting data. Most chillingly, these storms reduce visibility to absolute zero. Imagine an astronaut on the surface caught in the onset of such an event. The horizon vanishes. The sun disappears, their world shrinks to the dim glow of their suit lights reflecting off a swirling, impenetrable wall of dust. Navigating back to a habitat just a few hundred yards away could become an impossible task, a deadly game of blind man's bluff played against a freezing, suffocating environment. We have already witnessed the destructive power of a global storm. In 2018, one such event ended the 14-year mission of the Opportunity rover. The veteran machine, designed to survive a 90-day mission, had weathered many storms before, but this one was different. The dust blotted out so much sunlight that the rover's solar panels could not generate even the tiny trickle of power needed to keep its vital systems from freezing. Opportunity fell silent, its final transmission a poignant data point on the deepening atmospheric opacity. Months later, when the skies finally cleared, engineers sent over 1,000 recovery commands, listening in vain for a response. The rover was gone, its systems likely frozen beyond recovery, a monument to the sheer, enveloping power of the Martian environment. For future human explorers, a global dust storm would mean a complete lockdown. Surface operations would cease for the duration, which could be half a year or more. The crew would be forced to live on stored power and carefully rationed supplies, waiting in their dim habitat for a sky they could not see to clear. It is a reminder that on Mars, the weather itself is not an inconvenience, it is a patient planet-wide siege engine. And while the storm rages outside, another invisible force works to dismantle the habitat from within, born from the very chemistry of the red planet itself. The suffocating shroud of a Martian dust storm traps explorers inside, but the walls of a habitat cannot shield them from a more profound internal desolation. Cosmic loneliness is not just a feeling, it is a physiological and psychological state that could unravel the mind itself. This goes beyond the stress of confinement. It is the deep, aching reality of Earth deprivation syndrome. For all of human history, our species has lived under the comforting blanket of a blue sky, the rhythms of a 24-hour day, the familiar constellations, and the magnetic presence of a living world teeming with life just outside our door. In deep space, that blanket is ripped away. Earth shrinks from a majestic marble filling the viewport to a mere star-like point of light, a pale blue pixel lost in the black. The psychological impact of watching your only home, the cradle of all human experience, recede into insignificance is impossible to fully simulate or prepare for. It severs a primal tether. Astronauts on the International Space Station speak of the powerful, life-affirming overview effect, but on a multi-year journey to Mars, that awe can curdle into a hollowing sense of exile. You are not just away from home, you are watching home disappear. This profound disconnection can fuel a paralyzing existential dread, a questioning of purpose when you are a fragile speck in an infinite, indifferent void. The mind, deprived of its familiar anchor, may drift into a dangerous cognitive fog, where concentration lapses, motivation withers, and the monumental task of survival begins to feel meaningless. This mental erosion is compounded by a more subtle thief, the loss of Earth's timekeeping. Our bodies are hardwired to a 24-hour circadian rhythm, synced to the rising and setting of the sun. On a spacecraft, the sun rises and sets every 90 minutes, a useless, frenetic strobe light. Mission controllers impose an artificial 24-hour schedule with lighting, but the body's internal clock, its master circadian pacemaker, receives no true external validation. The result is a kind of permanent, low-grade jet lag that disrupts sleep patterns, impairs judgment, and degrades mood. Melatonin, the hormone that regulates sleep, can fall out of sync, leading to chronic insomnia or fatigue at critical moments. On Earth, we take for granted how the dawn tells our brain to wake and the dusk tells it to rest. In the sunless void between worlds, that gentle guidance is gone, leaving the crew's biology adrift in a sea of eternal sameness. The combined assault of Earth deprivation and circadian chaos creates a perfect storm for the mind, where the greatest danger is no longer outside the hull, but within the silent spaces of a crew member's own thoughts, wondering if anyone will even remember the pale blue dot they left behind. The void between worlds is not just a physical emptiness, but a legal one. Beyond the reach of any single nation's laws, space operates in a fragile framework of treaties written for a bygone era. The cornerstone is the Outer Space Treaty of 1967, a noble document born from the Cold War. It declares space the province of all humankind, bans weapons of mass destruction in orbit, and states that no nation can claim sovereignty over the moon or another planet. For its time, it was visionary, but today, as commercial companies plan lunar hotels and nations-eye asteroid mines, its limitations are glaring and dangerous. The treaty is famously vague on critical details. It says nations are responsible for the activities of their private companies, but what does that mean in practice? If a satellite from one country's corporation accidentally collides with a military satellite from another nation, creating a cloud of deadly debris, who is liable? The legal battle could rage for years on Earth, while the actual debris threatens every spacecraft in that orbital lane. More chillingly, the treaty offers little guidance for human conflict off-world. What is the protocol if astronauts from two rival nations living on the same International Space Station have a violent disagreement that threatens the mission? Are they subject to the laws of their home countries, the laws of the nation that registered the module they are in, or some new, untested concept of space law? There is no clear answer, no cosmic sheriff to call. This ambiguity becomes a powder keg when we consider resource extraction. The treaty prohibits national appropriation but says nothing about private ownership of what you dig up. If a company lands on an asteroid brimming with platinum and begins mining, do they own those materials? Can they claim the mining site itself to prevent competitors from moving in? The current answer is a resounding maybe, guided by a patchwork of national laws like the United States Commercial Space Launch Competitiveness Act, which grants citizens the right to own resources they obtain. But if another country passes a conflicting law, we could see competing mining robots from different nations arriving at the same valuable asteroid, with no agreed-upon rules of engagement. This legal vacuum could transform the final frontier into a new Wild West, where disputes over property and liability are settled not in courtrooms, but through technological sabotage or strategic crowding of orbits. It risks allowing terrestrial tensions to spill into the cosmos, turning a realm of potential cooperation into just another theater for human conflict. And in a dire emergency where every second counts, this gray area could paralyze a rescue. If an international crew is in distress, would political posturing over jurisdiction and cost delay a life-saving launch from another country? The laws we lack may one day prove as deadly as any radiation belt. The legal void of space is a danger of human making, but the environment itself wages a quiet chemical war against everything we build. Danger 25 is a slow, relentless corrosion in the space environment. This is not rust in the traditional sense, but a far more aggressive and alien form of decay. In the thin upper reaches of Earth's atmosphere, a spacecraft encounters a surprising threat: atomic oxygen. Up here, ultraviolet radiation from the sun is so intense that it splits ordinary oxygen molecules, O2, into single, highly reactive oxygen atoms. These atoms are ravenous to recombine, and the surface of your spacecraft is their closest target. When atomic oxygen slams into materials like silver electrical contacts or certain polymers, it doesn't just coat them, it chemically binds and carries them away, a process called oxidative erosion. Over months and years, this can thin critical thermal blankets, degrade reflective coatings, and eat away at wire insulation, a silent molecule-by-molecule dismantling. But atomic oxygen is just one soldier in this corrosive army. Ultraviolet radiation itself, unfiltered by any atmosphere, acts like a powerful bleach and a saw. It has enough energy to break the long-chain molecules in plastics, paints, and composite materials. You can see this effect on the flags left on the moon by the Apollo astronauts, their vibrant colors bleached bone white by decades of unimpeded solar ultraviolet exposure. On a functional spacecraft, this photodegradation makes materials brittle. Rubber seals lose their flexibility and crack. Window tints and protective coatings slowly break down, clouding over and losing their ability to reflect heat or radiation. The true danger, however, comes from the combination of all these forces, a synergy of destruction. The vacuum prevents any protective oxide layer from forming naturally on metals. The relentless thermal cycling, expanding and contracting materials thousands of times, creates microscopic stresses and cracks. Radiation pours into those tiny flaws, further breaking molecular bonds. Then atomic oxygen seeps in, attacking the freshly exposed surfaces from within. It is a perfect slow-motion storm that engineers must anticipate with every material choice. The white tiles on the space shuttle, the gold foil on satellites, the specialized paints on the International Space Station, all are carefully selected and tested to withstand this multifaceted assault for as long as possible. But there is no perfect defense, only a calculated delay. For a station meant to last decades or a generation ship bound for the stars, this slow corrosion is a hidden countdown clock, ticking away as the very skin of the vessel is subtly, inexorably eaten alive by the environment it was built to survive. Corrosion attacks the ship from the outside, but inside, a different kind of contamination builds with every breath and every meal. Managing human waste in space is a problem of biology, engineering, and sheer volume, a silent danger that grows more pressing with each passing day. On Earth, our waste is carried away by vast, invisible infrastructure. In a sealed spacecraft, it has nowhere to go. The air you exhale is laden with carbon dioxide, a gas that becomes a silent killer at concentrations as low as 3%, causing headaches, confusion, and eventually suffocation. To survive, every spacecraft must have a flawless system to scrub CO2 from the atmosphere, usually using materials like lithium hydroxide or more complex regenerative systems. A failure here is not a slow decline, it is a rapid, stealthy poisoning of the crew's shared air. Water presents an even more intimate recycling challenge. On the International Space Station, about 93% of all water is reclaimed, including moisture from sweat and breath, and yes, from urine. The system distills, filters, and purifies it back into clean drinking water, a technological marvel that is also a single point of failure. If the water recycler breaks down, the crew's supply would dwindle alarmingly fast, forcing emergency rationing in a matter of days. But the solid waste, the biological byproduct, is perhaps the most viscerally challenging. It cannot be simply ejected overboard, as that would create a cloud of hazardous debris orbiting alongside the spacecraft. Instead, it is stored, compacted, and sealed away. For a mission to Mars, this means living for years in a confined metal tube with a growing stockpile of your own biological refuse. The biohazard risk is constant, threatening contamination, and the potential spread of pathogens in an environment where even a minor illness can cascade into a crisis. On a planetary surface like Mars, the disposal problem becomes a profound environmental question. You cannot simply bury it and forget it. Introducing terrestrial microbes from human waste into the Martian soil would be a catastrophic act of forward contamination, ruining any chance of studying the planet's pristine biology. Any base would need a completely contained, industrial-scale waste processing facility, likely using high-temperature incineration or chemical breakdown to sterilize everything before it is stored permanently. The systems that handle our most basic bodily functions are therefore among the most critical on any spacecraft. They are the unglamorous, utterly essential plumbing of life, and their quiet, continuous hum is the sound of survival. A single clog, a pump failure, or a chemical imbalance can transform the habitat from a home into a toxic trap, proving that in space, the greatest threats are often the most mundane. But the most critical sensors are often the most delicate. Danger 27 is the terrifying prospect of a spacecraft going blind and deaf. In the void, a ship has no windows in the traditional sense. It sees the universe through a suite of exquisitely sensitive electronic eyes, and if those eyes fail, the mission is instantly, profoundly crippled. Consider the Star Tracker, a device no larger than a shoebox that is the spacecraft's ultimate compass. It takes images of the star field and compares them to an onboard catalog to determine the ship's precise orientation in three-dimensional space. Without this constant, silent reference, the craft loses its sense of up and down, left and right. It cannot point its solar panels at the sun for power, its antennas at Earth for communication, or its engines in the correct direction for a course correction. It becomes a disoriented child spinning helplessly in the dark. These optical sensors are supremely vulnerable. A single micrometeoroid impact, smaller than a grain of sand, can pit or crack a protective lens cover, scattering light and distorting the image. Contamination is another silent killer. Outgassing from interior materials or even a stray molecule of lubricant can slowly deposit a thin, greasy film on the optics, dimming their view over time. And then there is radiation. The constant bombardment of high-energy particles can slowly degrade the sensitive charge-coupled devices, the CCD chips that are the digital retinas of these cameras. Pixels begin to die, creating dead spots in the image. the cumulative noise increases, making it harder to pick out the faint pinpricks of stars against the black. The same threats target communication dishes, the ship's ears and voice. A damaged or misaligned high-gain antenna cannot lock onto the distant signal from Earth, severing the lifeline of data and command. For a robotic probe at the edge of the solar system, this is a death sentence. It becomes a silent, drifting monument, its discoveries forever trapped inside its own memory. For a crewed mission, the stakes are existential. Losing navigational sensors means you cannot find your way home. Losing communication means you cannot call for help. And losing the scientific instruments means the entire purpose of the voyage, to see and measure the unknown, evaporates. The spacecraft becomes a hollow shell, carrying living cargo through an infinity it can no longer perceive, a metal coffin with a beating heart inside. We armor the hull and shield the crew, but we must also protect these fragile silicon senses, for in the absolute black, to lose your sight is to be truly, irrevocably lost. The sensors that guide a spacecraft are its lifeline, but the funding that launches it is another fragile tether, one anchored entirely in the volatile soil of public opinion. Every mission that leaves Earth carries a hidden economic and political payload far heavier than any physical component. A catastrophic, high-profile failure, especially the loss of a crewed mission to Mars, would not just be a human tragedy. It would be a financial and cultural earthquake that could halt human expansion into the solar system for a generation. This is the 28th hidden danger, the economic sword of Damocles that hangs over every launch. The modern space program is funded by taxpayers, and their support is not guaranteed. It is a delicate trust built on a narrative of heroic success and scientific triumph. A disaster broadcast live to the world would shatter that narrative in an instant. The public and political backlash would be immediate and fierce. Congressional hearings would demand answers, budgets would be slashed, and the overarching vision of human spaceflight would be branded a reckless, expensive folly. We have seen this pattern before, though on a smaller scale. After the Space Shuttle Challenger disaster in 1986, the entire shuttle fleet was grounded for almost 3 years while the system was overhauled. The loss of Columbia in 2003 led to the decision to retire the shuttle program entirely, creating a gap in American crewed spaceflight capability that lasted for nearly a decade. These were national tragedies that reshaped an entire agency's direction. A disaster on the scale of a Mars mission would be orders of magnitude more devastating. The political will to fund such an audacious, risky endeavor would evaporate. The immense capital required, hundreds of billions of dollars over decades, would be redirected to safer, more terrestrial priorities. The paradox here is profound and dangerous. The mission to send humans to another world is by its very nature an exercise in managing extreme risk. Yet the agencies that plan these missions operate under immense pressure to avoid any risk that could lead to a catastrophic public failure. This creates a perverse incentive that can shape mission planning in subtle, potentially more dangerous ways. Engineers might be pushed to choose overly conservative, proven but obsolete technology over more advanced, efficient systems that carry a slight unknown. Bureaucratic layers of review and safety certification can multiply, adding cost and delay without necessarily adding safety. The entire culture can shift toward risk aversion, which in an endeavor where the baseline risk is astronomically high is itself a form of risk. It can stifle the very innovation needed to solve the problems of deep space travel. The mission becomes a prisoner of its own budget, forced to promise absolute safety in an environment where absolute safety is an impossibility. This economic danger means that the greatest threat to reaching Mars may not be a micrometeoroid or a radiation storm, but a loss of nerve back on the home planet, a collective decision that the price in both treasure and potential tears is simply too high to pay. That economic and political pressure demands perfect foresight, a map of every possible peril, But the cosmos holds a deeper, more unsettling truth. The 29th hidden danger is the most formidable of all, the unforeseen unknown unknowns. These are not the problems we have identified and are working to solve, like radiation or bone loss. These are the gaps in our understanding so profound, we do not even know the questions to ask. Space is not merely a harsh environment, it is an alien one, operating on physics and chemistry under conditions we can only partially simulate on Earth. Our experience is a tiny, fragile data point in an infinite laboratory. The history of spaceflight is punctuated by these sudden, bewildering encounters with the unexpected. Consider the Gemini 8 mission in 1966. Pilots Neil Armstrong and David Scott had just completed the first successful docking in space, a monumental achievement. Moments later, their spacecraft began to spin violently. They were tumbling end over end, faster and faster, a dizzying whirl that threatened to tear the craft apart or render the crew unconscious. The pilots, with incredible coolness, diagnosed a stuck thruster on their Agena target vehicle and undocked, but the spinning only worsened. An unknown unknown had revealed itself. A short circuit in their own spacecraft's orbital attitude and maneuvering system had caused a thruster to stick open, firing continuously. This was a failure mode no one had anticipated. Armstrong, fighting disorientation and graying vision from the centrifugal force, had to shut down the entire primary control system and activate the separate re-entry control thrusters to finally stop the spin. They had mere seconds of fuel left. The mission was aborted, but they survived because of human ingenuity in the face of a complete surprise. That is the essence of the unknown unknown. It is the thruster that fails in a way the blueprint said was impossible. It is the material that behaves differently after 3 years in zero gravity than it did in any 6-month test. It is the psychological reaction to a prolonged solar storm that no isolation study could predict. For a journey to Mars, the list of unknown unknowns is terrifyingly long. How will the complex interplay of radiation, microgravity, and isolation affect human cognition over 30 months? Could a novel chemical reaction occur between the Martian soil and our habitat's materials, producing a toxic gas? What unforeseen flaw might appear in a closed-loop life support system that has never been run for 1,000 consecutive days? We can build redundancies for known failures, but we cannot build a backup for a gap in our own imagination. The greatest peril for the pioneers who venture farther than any human has ever gone may not be the storm we see on the horizon, but the shadow we never knew was there. It is the silent law of physics or biology that waits undiscovered for our arrival. The unknown unknowns remind us that our greatest ignorance may lie in our own power to change things. This brings us to the 30th and final hidden danger, a burden not of physics or biology but of conscience. It is the moral weight of planetary change. As we stand on the brink of becoming an interplanetary species, we must confront a profound ethical question that accompanies our tools and our ambition. Do we have the right to fundamentally alter another world? For decades, science fiction has painted visions of terraforming, of melting Martian ice caps to create seas and thickening the atmosphere to walk without a suit. It is a grand, epic dream of making a dead world live, but the process would be neither clean nor gentle. It would involve planetary-scale engineering, perhaps by redirecting comets to deliver water, or building giant orbital mirrors to heat the surface, or seeding the atmosphere with potent greenhouse gases. The goal is noble, to create a second home for humanity, yet the act itself is one of staggering violence against the existing Martian environment, no matter how barren it appears. We would be imposing an Earth-like template on a landscape that has evolved under its own rules for over 4 billion years. And here lies the central ethical dilemma: what if Mars is not truly dead? Our current understanding suggests it is a frozen, radiation-blasted desert, but we have not yet searched every crevice, every deep aquifer. The potential, however faint, for indigenous microbial life hidden beneath the surface is the single greatest scientific discovery we could ever make on that planet. It would be a revelation that reshapes our understanding of life in the universe. Terraforming would be its death sentence. The warming climate, the introduction of Earth microbes, the flooding of potential habitats would almost certainly obliterate any native Martian biology. We would be committing a form of cosmic genocide in the name of our own survival. Even if we conclusively prove Mars is sterile, the ethical questions do not vanish. Do we have the right to erase the geological record of another planet, a pristine archive of solar system history, to build factories and cities? Will our expansion look like exploration, or will it look like conquest and extraction, repeating the worst patterns of our history on Earth but on a planetary scale? This is the hidden burden that comes with our technology. The rockets and habitats are just hardware. The true test is the wisdom we pack alongside them. We are on the verge of gaining the ability to reshape worlds, but we have not yet forged a consensus on whether we should. This final danger is not one that can be solved with thicker shielding or a better exercise machine. It is a question for all of humanity. As we reach for the stars, we must decide what kind of gardeners or what kind of bulldozers we truly want to be. These 30 hidden dangers paint a staggering portrait of the cosmos, not as a serene expanse, but as a relentless gauntlet. From the microscopic bullets of galactic radiation shredding our DNA to the cosmic scale loneliness that unravels the mind, every step beyond our atmosphere is a negotiation with peril. We battle toxic dust, silent vacuum, and the very laws of physics that govern our rockets. We confront not just environmental extremes, but the profound ethical weight of becoming a multi-planet species. This is the unvarnished truth of space exploration, a venture where triumph is measured in inches gained against an infinity of threats. Yet here lies the paradox that defines our species. This journey is humanity's greatest adventure precisely because it is so perilous. The magnitude of the danger is what gives the endeavor its meaning, its nobility, and its irresistible pull. To turn away from these challenges is to deny a fundamental part of what it means to be human, to be curious, and to reach for a horizon simply because it exists. Understanding these 30 dangers is not a counsel of despair. It is the essential first step in the meticulous, courageous work of overcoming them. Each problem identified is a puzzle to be solved, a lock for which we must forge a key. It is through this clear-eyed confrontation with the void that we will innovate, adapt, and ultimately learn to not just visit the cosmos, but to belong there. So we leave you with a question and an invitation. Which of these hidden dangers surprised or fascinated you the most? Was it the psychological abyss of Earth deprivation, or the silent corrosion eating away at our ships? Share your thoughts in the comments below and join the conversation about our future among the stars. If you found this deep dive into the mysteries and perils of space compelling, be sure to subscribe. Together, we will continue to unravel the greatest unknowns, one hidden danger at a time.